Hi, welcome to the lesson about different data store implementations. In this lesson, we are going to see three of the state store storages, state store storage implementations that I presented in the theory lesson. I will start by the in-memory state store, but before that, I need to bootstrap, I need to start Docker containers. And of course, one of the data stores will be the remote data store based on CDB, and that's why I will have to create some context for the execution. So just maybe before it starts, I will show you the queries. So it's just a key space creation with a state store table composed of state ID and state payload with TTL configuration. So that's nothing complex. Okay, it's loaded, and let me start with the in-memory state store. I have, as usual, a data generator file that will bootstrap an Apache Kafka topic. It's important to notice that it's worth noticing that this topic has two partitions, because I will show you that one of the main drawbacks of a local state store that is the lack of persistence in case of state redistribution. And later inside I'm creating 3 rows each time, and I'm trying to allocate them for on different partition. As you can see here, I'm checking whether the letter is A or not, and I'm using a different partition number accordingly. And what about the state store itself? So the state store itself is a state, I would say stateless, but it's stateful because it has the states that is tied to the life cycle of the consumer. So it's a stateful consumer. And the state store is a simple hash map. So if you remember the lesson, I said that the state store can be a dictionary if you use Python, or a hash map or map if you use Scala JVM. Here I am using a hash map. And what is our state? Our state is a simple counter for each letter. So I'm taking exactly the same example as in the previous demo lesson, but this time I'm counting the number of occurrences per key. And in the end, I'm printing the execution every time. Okay, so now I will start the data generator. And I have my two consumers here ready for running just here. Okay, I created a topic, and logically, yes, we are generating the record. So let me start the first consumer. And the first consumer should be up and running very soon. Yes, we have our state. Each time, remember which time we send 3 records, so it's logical the count is the same for all of them. And what I'm doing now is that I will start another consumer. So as if you remember, if you start 2 consumers with the same group, they will share the load. So here the consumer, we can see that it takes the first partition, the partition number 0, because we have the A letters updated, and the A letters that are not updated anymore in this. But the problem is that this local state doesn't redistribute the state store correctly, because here we just allocated the partition, but the partition without the state store. And as you can see here, instead of 8, we should have something like 13 on 12 for the counter. And that's the main drawback of a local state store. It's quite easy to implement, isn't it? Because it's only a data structure that is native in your language, but the drawback is that it doesn't scale very well. So let me now stop this demo, and I will go to the in-memory state store, but with fault tolerance. Okay, I'm starting the project, and the project is similar to the project you saw probably in the stateful versus stateless demo. I'm sampling, let me just develop a bit. Yes, I guess you can see I'm doing a count for letters. Typically I'm generating the same input, and what I would like to show you here is that Apache Spark implements the in-memory state store with fault tolerance. So to show you the in-memory state store, I will just need to find some internal classes. So with a state. And this is our map to update. So there are different implementations, but under the hood you can see that in both cases is a concurrent hash map. So that will provide the data for Apache Spark while it executes the query. But once you stop the query, Apache Spark will load the state from the checkpoint location. So let me run the generator first, and later the stateful Spark consumer, and we will see inside the checkpoint location the files that store the state. Okay, its topic is created. I will start the consumer. Just copy paste the checkpoint location here. Okay, the counter is up and running. Let's wait a few more. Okay, 4. Okay, remember we have 4 items for each letter. So now I will go to the checkpoint location. And let's see what we have here. We have 5, I would say directories, checkpoint directories, where the first 4 are for the metadata management, so for the offsets for the data that is consumed and for the incoming data, in fact. Whereas in the last one, you have the famous state store, and if we print the structure, you can see that we have one sublocation per shuffle partition, and inside each inside each location we have a delta file, and delta file contains only all the updated values in the given microbatch. So if the state doesn't get any update for like 10 microbatches, it won't be stored in 10 delta files. It will be stored only when it gets an update. So under the hood, Apache Spark also has a mechanism to compress these delta files into one single snapshot, and it's just to optimize the loading process that we are going to see just in a moment. And in that case, the content of all these files get merged into a single snapshot file, and when Spark needs to restart the processing with state, well, it will simply take the snapshot file. Okay, so yeah, we have this, and now what's nice about this fault tolerance is that if you don't change the checkpoint location, well, remember the count is 4, Spark can very easily reload the state and do not start from scratch, as it was the case, remember, of the in-memory only state store. So here we already generated a lot of records, but you can see that we are at 29 just in there. Just 30, okay, we just maybe count number here. Yeah, we have 31, so we were about to counting the 31 first record. Okay, so that was for the stateful of the in-memory state with fault tolerance for reprocessing. So here I gave you the example of Apache Spark. Apache Spark in the vanilla open source version doesn't support state redistribution. So if you add more shuffle partitions, or if you change number of shuffle partitions, unfortunately it will not work. But there are commercial distributions of Apache Spark, like for example Databricks, where the state store redistribution does work. That was just a short notice, a quick notice. So I will show you now the remote state store that will use ScyllaDB. So here the logic is a little bit much more complex because we had to implement it on our own, and we have to implement both in memory, so fast access, and fault tolerance. Fault tolerance that is provided natively by the primary state store storage, which is the ScyllaDB in our case. And again, we have here an Apache Kafka consumer with different group ID because I will like to show you that in that case it can distribute. And what we are doing here, we are deserializing the JSON to the letter with event time object that we are generating in generator. So the first step consists of getting the state entry for this letter, and we get it either from the in-memory cache or from the state store. In this state store, we check first whether we can load the state for the event time, and if not, we are trying to load it from the latest alias. Latest alias that is always written alongside the key. And yes, later we just checking the latest value if it's appropriate for the restore, and if not, we simply create a new state store entry. And that's for the load. Later we check whether we are processing other than the first occurrence for each key, because that way we can provide the state for the others. Let me just give you a quick example here. So let's suppose that we are processing the key number 1. Now our event time is for 10 o'clock. Okay, and so our state as now is only put into the local cache. We don't put it into the state store, remote state store empty, because it's our first execution for that key. Now when we get another event for event time of let's say 10:20, what we do first, so state is already in the cache, so we don't need to read it. Later we are saving state into the remote state store. We are saving it with this key, so 10:20, but we don't update the value. So if you check out this method, you can see that we just change the event time, but the value that is saved is the same as for the previous state, so typically here it's 1. And later we are doing our usual incrementation and stuff. Why we are doing that this way? So let's see what happens right now. Let's suppose that we have some failure in there for the event time number 10:20. So increment failed. So our consumer needs to restart, and now when the consumer restarts, it will simply take the state for 10:20, but with the count that was available in the beginning of the processing, so that the counter will be correct because of this kind of logic. I hope that it's clear. And now, yes, in the end we are doing the increment. We increment the counter, we update the state store cache, remember, and we are printing some debug for the numbers, for the count that we have just incremented. And as I said, all the state entries are written into a ScyllaDB. And what can I do now? Yes, I can start the data generator. I hope this will start very soon. Yes, we are creating the topic. Yes, we are generating the records, and now I will start the consumer. Okay, you can see that we have the counters that are incrementing, and just take a quick look at the Sila DB and at the look of our state store. You can see that we are doing that as I explained in the previous minutes. So now I need to start the second consumer. That you will see that just in a minute. That will take over the partitions or some of the partitions belonging to the first consumer. You see that it's now processing the partitions number the partitions where the data for B and C is located, and that it also correctly loaded it from the state store. And that's first, and here you can see that this consumer only continuously processes state store for the letter number A. And what happens if I stop one of these consumers? So let me stop this one. Logically, after some time, we should get the redistribution action from Apache Kafka and process all these three keys again in the same consumer. So let's wait a few times before the rebalancing happens. And you can see that it happened right now, and we start processing the B and C from the last entries. And that's one of the main pros of having this remote state store versus having a local state store. Of course, for me, the easiest way and maybe the recommendation I would like to give you for stateful processing is to rely at most as you can on bulletproof solutions. So namely the data processing frameworks like Apache Spark, Apache Flink, also Dataflow if you are using GCP, because all of them have already all this state management plus fault tolerance implemented. You don't need to worry about anything else but writing your stateful logic. If you do choose in memory or remote state store because you don't want maybe to learn these frameworks, well, that's fine in your context, but be aware of different gotchas that you may face. Remember, in memory only state store doesn't work well when you want to scale your application and when you want to restart it, for example, because of a failure. On the other hand, the remote state store covers these two cases, but it has writing the fault tolerance logic may be a little bit tricky. And that's all for this lesson. So thanks for watching and see you in the next one.